My name is Erik Bartsch. I'm with VerdeGo Aero and been in the electric flight business for quite a while now, since probably before it was cool or interesting. And I've presented a few times at the forum before, and what I thought I'd cover this year is a bit of a contrarian view of what's going on in electric flight, to talk about some of the misconceptions that are out there and how they impact how we think about what's possible with electric flight, but also how they maybe cause us to miss some of the important things that are happening behind the scenes with electric flight. Because there's a lot going on, there's a lot that's really compelling, there's a lot that might not be so compelling as it turns out, and then there are quite a few things that are misunderstood about the distinction between the two of those. So I'm going to go through the presentation that I'd like to, I'll be asking for audience participation at times, but for the rest of the questions, if we can save those for the end, be happy to address them afterwards. So my own history with electrification of flight, there are really a few different phases of it. Going back, probably 15 years now, I was involved in the electric flight industry at a really small scale, worked with a great team at Horizon Hobby, and led a group of people that put about 4 million small aircraft into the air over those years. So we like to say that our production outstripped the entire full-scale aviation industry by many orders of magnitude. And the majority of those were electric. And so that was an interesting phase. There are some things that scale up from that. There are some things that really don't scale up from that. I later was involved with full-scale electric flight. I actually got to log some flight time in some of the early battery electric aircraft, got some hands-on experience with those technologies. Learned a lot about what's great about electrification and learned quite a bit about what's not great about electrification. And as with any technology, it's a tool, can be used for the right things, can be used for the wrong things. And then more recently, I'm one of the 3 co-founders of VerdeGo Aero, a propulsion company that is developing hybrid electric power systems for the electric aircraft market. And I'll go into some of the rationale behind why we do what we do and why that's compelling for certain markets. And along the way, I've done a lot of flying in basically any type of aircraft I can get my hands on. I'm a decent fixed wing pilot. I'm a terrible rotary wing pilot, not yet licensed there, but aspire to be it eventually. So if we think about what's in the news, how many people here have seen headlines, like unbelievably large headlines about electrification in the media? I know I have. My favorite here is $1 trillion by 2040. I will say, as someone who runs one of the businesses in this market, I really hope that's true. I don't believe that for a minute, but if that plays out, I would love to be wrong. There's a lot of hype out there. There are a lot of people saying, okay, this is going to change everything. This is, there are billions of dollars flowing into companies in this space. Some of that's going in really good directions. Some of that may not be going in good directions. And so part of why I'm here today, and I think part of why you're here today, is to talk about how do we figure out what's real and what's really going to come next in electric flight, and maybe sift through all of this to find those nuggets of wisdom. So here's the first audience participation question. Are these two things the same? No. What's the thing up here, the blue thing? It's a car. What's the thing over there? It's an airplane. These are not the same thing. Now, that wasn't very hard to figure out. And they're not the same for a whole bunch of reasons. Cost, weight, technologies, business model, manufacturing, regulation, performance. There's really not much in common between these two things, other than the fact that they do have internal combustion engines. So I'll give them that. So, why do people think these things are the same? That's a really good question. I'm going to get to that. More accurately, I'm going to get to why I don't think these things are the same. But right here we've got a Tesla. Teslas are great. I've driven them. They go really fast. They've got pretty good range. It's a car. I'll give them a moment. Over here we have one of the notional drawings from the Uber Elevate program of what an electric aircraft might look like. These things are not at all the same, yet there's been a lot of the early era of the electrification of aircraft where you can sum it up by Tesla did really cool things with electric cars, so we want to now do really cool things with electric airplanes. And the logic kind of stops there. And it's important to acknowledge that these are not at all the same things, although electrification has a role with both of them. So what we know about electrifying and even hybridizing cars is not particularly relevant to what we do to electrify or even hybridize an airplane. Electrification is very relevant for aviation, but it's going to play out quite a bit differently. So, what are these? Tools. So we've got, what's that? Hammer. Exactly. These are all tools. So batteries, electric motors, and electrification itself are all technologies and technology tools that we can use in a variety of aircraft markets. When they're used for what they're good for, you can have amazing results. When they're improperly used, it's like banging on a bolt with a hammer. It's not going to work. And there are billions of dollars of hammers banging on bolts right now. And that's something that's just not going to work. And so when tools are used properly, they're great. When they're used improperly, not so great. All right, so a couple disclaimers as I go into the main part of the presentation. There are a huge number of aircraft designs, missions, and use cases that are out there. And one of the really cool things about the current phase of the aerospace industry is that we're in a bit of a divergent phase. People are back to trying new things that may or may not work. We've got hundreds of companies going in different directions with electrification. That's a very good thing. It's a necessary thing in the early stages of adopting a new technology. And so there's a big diversity of use cases and examples out there. My presentation today is about how electrification is likely to play out on a large scale, what the biggest opportunities and the biggest markets are. That doesn't mean that there aren't a few corner cases that violate some of the rules that I'm going to talk about. There are some. I could do a whole separate presentation on weird corner cases where there are exceptions to the rules that I'm talking about. But today is talking about the biggest opportunities and the biggest trends that we ought to watch in the electrification space, and why some of the things that we may all be paying attention to now might not be the right things to pay attention to. So when we think about aircraft propulsion, there have really been two major revolutions in aircraft propulsion in about 120 years. One was the piston engine, because before the Wright brothers had piston engines, we had gliders. And I think we can all agree that once we had piston engines in airplanes, we had transformations in what they could do. And I'm a sailplane pilot, I love gliders, but you can do a whole lot of different things with a powered aircraft that you can't do with a glider. And then along through the 40s, 50s, and 60s, the jet engine appeared. And that once again created a transformation in what you could do with an aircraft. And electrification, we're at the outset of a third major revolution in aircraft propulsion, but it's going to play out very differently than how it has in the automotive industry. So this is another audience participation question. That airplane there, you can't see the power plants or the propulsion system in any way. Is that a jet or is that a piston engine aircraft? It's a jet. That's correct. It is a jet. All right, you can't see the propulsion system here at all. Is this a jet or is this a piston engine aircraft? It's a piston. All right, can't see it here again. Is this a jet or a piston? Jet. Piston, exactly. All right, that's a rocket. That was a trick question. But the amazing thing we did, and you could show these to the average person on the street. This is an aviation enthusiast audience. We know a lot about aircraft. Many of you can probably name every single aircraft I showed there and talk about the history of it. What's interesting, though, is we saw all those aircraft. We didn't see the propulsion systems. You know by looking at the airframe what kind of propulsion it is, because the power plant impacts how the aircraft looks, how it's configured, how it's structured, and what it can do, what the missions are. So the optimal airframe for one type of propulsion is usually a bad fit for other means of propulsion. So now we have all these crazy looking things, and I'm in the electrification industry, but I can still say some of the things we're working on look a little bit crazy to those of us that have been in aerospace for quite a while. But these all look different. These don't look like jets. These don't look like piston engine aircraft. There are reasons for that. That actually makes sense. And so misconception number one, I said there were going to be 10 of these, so I've got to get through 10, is that electric aircraft are somehow going to look like conventional aircraft, but they're going to have batteries and motors. Propulsion revolutions lead to revolutions in how you design the aircraft. And electric aircraft should look like electric aircraft, just like a jet looks like a jet. There are reasons for why piston engine aircraft, jets, and now electric aircraft are all going to look very different. And over the next decade, we're all going to get a lot more used to looking at things. And just as we all picked out what the jets were and what the piston engine aircraft are, there are things that lend themselves to being done with electrification. And we have to keep in mind, and I've showed this slide before, this is one of my favorite Photoshops, putting electrification on the wrong airframes is kind of like saying turbofans are great, Cessna 172s are great, so they'd be even better with a turbofan. You could do that, I'd even fly it, but I guarantee you it would be a worse airplane in every aspect, whether it's useful load, efficiency, noise, you name it. That would be a bad aircraft. A Cessna 172 should have a piston engine in front. So that's probably not the big idea, and we shouldn't do that with electric motors. So another audience participation question. What part of electrification is visible in these aircraft? Any insights into that? Anyone want to yell anything out? So I heard propellers, I heard electric motors, multiple electric motors. I like that one. So what you can see here, you notice nobody said batteries because batteries aren't actually visible in any of these aircraft. But what is visible is you've got a bunch of electric motors scattered around an airframe doing different things. In some cases, we're managing the airflow over the whole wing. In some cases, we're converting from vertical flight to horizontal flight. But you can see that all of these aircraft are built around having a bunch of electric motors. And that's different. That's something that we don't typically see with piston engines or turbine engines. So there's a reason for that. Electric motors are amazing things. They are responsive, they're lightweight, they have unique torque curves, they can run at really low RPM, they can run at high RPM. They scale in size differently. It's actually practical to have a whole bunch of electric motors and not one or two big ones. They're reliable, simple, low cost, and we have high performance solutions right now. These technologies exist. There are a bunch of companies out there that can make great electric motors that you can put on an airplane. And I would say electric motors are the biggest idea out there in electrification. That is the enabling technology that makes electrification interesting. Next on the list, power transmissions. There have been a lot of really interesting experimental aircraft programs done, particularly in the 50s and 60s, when it came to convertible aircraft designs, things that could fly vertically and horizontally. the Achilles heel of almost all of those programs was both control as well as mechanical complexity. There were drive shafts and gearboxes and all manner of systems to transmit the power around those airframes. And the result is a really complex, really unreliable powertrain. And those aren't particularly good things in an aircraft. Moving electricity around an aircraft is a lot less complex than moving mechanical power around an aircraft. And that's really important because if we look at those aircraft on the far side over there, they all have a whole bunch of different propellers around the aircraft. We have to get power to all of those. If we tried to do that with drive shafts and gearboxes and everything, you wouldn't want to build any one of those. So misconceptions 2 and 3 about electric flight are that batteries are the biggest innovation and that it's all about batteries, because actually electric motors are the most exciting technology that really allows us to design new types of aircraft. And electric power transmission is next behind that on the list, because that allows us to have these new configurations also, where maybe instead of 1 or 2 propulsion units, we want 8 or 10 or 20 because we want to control airflow in all of those places. So leveraging motors and electric power distribution is what opens up these new design spaces for aircraft designers to do things they couldn't do at all before or couldn't do practically. So I said batteries at best were number 3 on the list. How fast are batteries improving? And that's a question that I think there are even some other forums about that are going on over the course of the week. I've been doing this for more than 10 years. I've been watching this closely. I've worked on battery-powered aircraft, and so there are a few terms that we run across all the time. One is you'll hear people talking about energy density. And what that really means is the weight of a battery that has a given amount of energy inside it. And we tend to measure that in watt-hours per kilogram. And what that means, if we convert that into things that are closer to the terms that we work with in aviation every day, 750 watt-hours of electricity is about a horsepower for an hour. So if you store that much, you've got a horsepower for an hour. Batteries are currently somewhere between 200 and 300 watt-hours per kilogram, depending on the technology. And 200 watt-hours per kilogram means you've got a little more than 1/10 of a horsepower for an hour for each pound of batteries. So if you start multiplying that out, you don't get to very impressive amounts of horsepower for any kind of duration for the batteries that we've got to work with on the market. And so that's a problem. And it's a problem particularly for missions where we want to go far, fast, or with heavy payloads. So one of the things that I've been tracking and kind of keeping my own files on, so this is admittedly a little bit anecdotal data, is the promises that I keep hearing every year for what's just around the corner. So that's this big bubble up here on the graph where, there are always these breathless announcements that next year we're going to have an amazing battery cell that's going to do X or Y, and it's going to be incredible and you're going to love it, and it's not quite out yet. And that's been happening to me for more than a decade. And I used to put a lot of faith in what I saw in those press releases. I've become a little bit jaded over the years, though, because this line at the bottom, that's what I've actually been able to buy every year. So the good news is it's going up, so that's better than if it were going down. It's not going up very fast, though, and this line is very different than all of these claims because it's really hard to store large amounts of electricity in chemistry and to figure out how to do that reliably, get it into a supply chain, make it safe. I don't want to minimize how hard this is for the chemistry researchers that are working on it, but the reality is something that's different than what we perceive in all of the announcements that we see. So misconception number 4, that batteries are closing this weight gap quickly. They are not. Moore's law for battery energy density is that they get better at 3 to 5% a year. And that's been the case for a really long time. And I don't see that that's changing. And what that means is it takes anywhere from 14 to 23 years to double performance. And right now, liquid fuels are at least 20 times more energy dense than a battery. So what if a Cessna 172 had 2.8 gallons of fuel in the tanks instead of 56 gallons in the tanks? How useful is that plane? How many people in the audience want to take off with 2.8 gallons of fuel on board? I don't. I'll do a lot of things with aircraft, but that doesn't sound particularly fun. So, all right, batteries, they haven't progressed. Let's set aside what I just talked about. Let's say, all right, yeah, but what if one of these things that's been announced about energy density comes true and batteries get a whole lot lighter? Is energy density the only thing that's holding us back, or is that just the thing we talk about the most? Well, there are a lot of things that are actually holding us back. Energy density gets the attention because there's a factor of 20 problem there. But I will say that if all we had in aviation were batteries, and someone ran in with a gallon of jet fuel or avgas and said, hey, check this out, I've got a different way to package energy, they'd get a Nobel Prize. There'd be a statue over there in the center plaza of AirVenture for them. So liquid fuels get lighter as they are used. Batteries don't. You can trade energy for payload. I think a lot of us in the room that are pilots, sometimes you take off with fuel to the tabs so you can put an extra person in the plane. There is no such thing as filling a battery to the tabs when it comes to weight. It weighs as much whether it's empty or full. The last drop of fuel is as good as the first. Batteries have a particular issue here where as they drain, you can't pull power out of them to the same degree that you could at the beginning of the charge. That's a big problem because as pilots, we're used to consistency. We like to make sure that at the end of the flight, the powertrain behaves as well as it did at the beginning of the flight. Charging infrastructure, you can charge a liquid-fueled aircraft at pretty much any airport. It's a fuel pump or it's a fuel truck. I don't see a lot of charging stations. There are a few out there, but there's a big infrastructure gap. We already covered the 20 times lighter. The technology is certified. The supply chain exists at scale for liquid fuels, and liquid fuels cost a lot less than batteries. So energy density is not the only issue we face looking at batteries. It's not even the biggest one in some cases. And the one that I've experienced firsthand as a pilot in the air in a battery electric aircraft, that last drop being as good as the first, that's a really hard one to solve in a battery. Even if you had equal energy density between liquid fuels and batteries, some of these others are really big Achilles heels for using a battery to be the primary way you store the energy in an aircraft for its mission. So we got to watch that one closely. So misconception 5. Batteries just need to get lighter and then it all works out magically. It doesn't. Batteries need to get better in a whole bunch of ways if we want to use them as a primary energy source in aviation. I'll get back to that one in a few minutes here, but that's really important. So, what about really, really short flights for battery-operated aircraft? That's something we talk about a lot. Well, if we just want to go a really short distance, let's just start there, because then that's all going to work out. So we're going to do these short hops. We'll leave the long flights till later. We'll push that one down the road. Well, we can't just plan energy on an aircraft for where we're going to go. We have to think about energy reserves. We need to think about derating in the case of a battery because you can't get to all of that energy. We need to think about flight planning reserves. Are we going to be able to go in a straight line or not? We need to think about the aging of the battery. You know, as I mentioned, the battery effectively shrinks every time you use it. You know, it's like you've got a fuel tank that shrinks a little bit every time you fill it up and drain it. Well, we've got a flight plan and write the manuals for the aircraft as if the battery's at the end of its life, not the beginning of its life. So the problem is that all of this other stuff is the same whether you're flying a really, really short flight or a really, really long flight. And that gets us into these weird design spaces where, you know, our team and we've looked at design cases where your energy reserves all of a sudden are 10 times what your mission is. And that's something we've never really dealt with before in aviation. We're always used to the mission is the majority of the energy, and then you've got, you know, some reserve that you add on to the end for safety. That can get flipped completely. If you're looking at these really short missions, the rest of this stuff becomes huge, and you may have a 5-mile flight that requires 150 miles of extra energy on board to be legal and safe. So, misconception number 6, operating a really short flight gets around the limitation of batteries. And it does to an extent, but perhaps not enough to really help us do the things we want to do. And we wind up with a whole lot more reserve energy than mission energy. So, if batteries aren't able to deliver the mission capability that we want in the aircraft, then is there a point to electrification at all? Should we abandon this and go in a different direction? You know, if there's a 20 times energy deficit, why would we bother doing this? That's an interesting question. It's especially interesting for those of us that work in this industry. So, unsurprisingly, I have some answers to that. So, there's some interesting motivations for electrifying an aircraft that allow you to design something you couldn't have before. And one of them is distributed electric propulsion. That's having a whole bunch of motors instead of 1 or 2 propulsion units. And that allows you to control the airflow and control the thrust over a lot of different places on the airframe. That's kind of interesting. One of the things you can do with that is you can merge together attitude control and propulsion. And every small-scale drone that's sold in the hobby industry, that's what they do. The attitude control, the pitch, yaw, and roll of that drone is driven by the same electric motors that drive the propulsion. And so all of a sudden you can blur the lines between those things. You can do active aerodynamics. You can control the boundary layer over parts of the aircraft. You can have different numbers of power generation and thrust units. You can, down here at the bottom, optimize for peaks and valleys of power. So you can optimize for steady state energy consumption in an aircraft versus the peaks that you might have on takeoff or climb of the aircraft. So there are some really interesting reasons that an aircraft designer might want to apply electrification in an aircraft, and these on this list are all driven by what electric motors and electric power transmission enables. None of those things have anything to do with batteries. So one of the things that then comes into play is the concept of a hybrid electric power plant. And as full disclosure, this is what my company VerdeGo works on. So I could talk forever about these, but I won't. So, but a hybrid electric power plant, liquid fuels go in, propulsive electricity comes out. And that enables the benefits of electric motors and electric power transmissions to be realized, and it gets around some of the mission-related limitations of batteries. And so these systems, whether they're designed around a piston engine or a turbine engine, they bring together a conventional piston or turbine engine, a motor generator, power electronics, control systems, the cooling and thermal management systems, And what you get is an integrated unit that can provide propulsive energy electrically and in some cases mechanically, depending on if it's a series or a parallel hybrid configuration. But that allows you to have these aircraft that depend on electric motors but have a lot more mission capability. And we've actually got one of these power plants on display at the Air Force's AFWorks Pavilion. That's booth 324 over near Garmin. And I would encourage anyone in the audience who's curious to see what one of these systems looked like to head over there at some point. So why might we want to hybridize an aircraft and put a hybrid power plant in an aircraft? And there's really kind of a simple equation that governs that. And that equation goes like this. If an aircraft design inherently has to be electrified, you can't have that architecture any other way. And so I've got some silhouettes of strange looking things that look like electric aircraft, and the mission requirements demand high performance, then using electric motors and power distribution in those aircraft is the only way you're going to get that aircraft. Using hybrids and liquid fuels is the way you get the mission capability, and that's how you make this whole thing useful, is you design an electric aircraft and you run it on liquid fuels, but you're getting an aircraft you couldn't have before, and you're potentially getting an aircraft that can do a mission profile that it couldn't do before. So, misconception number 7, batteries have to get a lot better before electrification is compelling. There are a lot of things we can do right now with technologies we have right now by applying hybridization, liquid fuels, electric power transmission, and electric motors. And in fact, there's a lot of exciting work going on for both military and civilian missions doing just that and combining these things together. And we don't have to wait 5 years or 10 years or 25 years for a technology to get better. We can combine technologies that exist now, building blocks, Legos if you will, we can plug them together in different ways to get things that are viable in the near future and not the far future. So, if we're using liquid fuels to power electric aircraft, why are we bothering with electrification? That seems to be a good question for us to ask ourselves. Why are we doing this? So remember this, it's if an aircraft design inherently has to be electrified and we want that high performance, then we do this. There are a lot of aircraft configurations that don't have to be electrified, and they probably shouldn't be. Let's go back to, I showed those slides that showed what a piston aircraft looks like, what a jet aircraft looks like, and now what a lot of these electric aircraft look like. So if it doesn't need to be electrified, maybe it shouldn't be electric. If it's a Cessna 172, maybe it doesn't need a turbofan. So it's the right tool for the right job. And at the same time, one of the big factors here is that when we look at using liquid fuels in an electric aircraft, there's a big trend that's going on right now in parallel with electrification, and that is sustainable aviation fuel. And that is a much bigger trend for the jet fuel market than the avgas market. But it's really a critical thing that billions of dollars of investment are going into creating manufactured liquid fuels that basically are jet fuel, but with a much lower net emissions profile. In a lot of these cases, what you're doing is you're pulling carbon out of the atmosphere when you make the fuel, you put it in the plane, you release it back into the atmosphere, and you keep going around that cycle such that you've got either very low or no net emissions. So the R&D for these fuels is largely done because they are certified. United Airlines, as an example, has already done revenue service flights with transport category aircraft with SAF in the fuel tanks. So this is certified, it exists. The big challenges for SAF are getting the supply chain large enough and the costs down low enough so that it's viable. But when we talk about liquid fuels, it's not just the liquid fuels we have right now. There are also the liquid fuels that we have in the future. And liquid fuels are a more convenient way to package energy than a battery as a primary source of energy. And so as we look at the gigantic value of all the infrastructure, all of the transport category aircraft, and the fact that SAF already has a huge momentum, I would say that SAF is an inevitability. We're going to see more and more of that, and that's already way down the path. Hydrogen and really energy-dense batteries are not necessarily an inevitability. They might play out, they might never play out. So remember this equation again, and I've modified it just a little bit. If an aircraft has to be electrified and we need significant mission requirements, then motors and hybrids and SAF allows you to get those benefits sustainably, and it brings together two things that are often thought of as separate directions in sustainable aviation: electrification and sustainable fuels. Those have separate paths that they may take. You may also see those come together in some applications and be two parts of a bigger picture. So, misconception number 8, electric aircraft are only driven by sustainability. You know, people often think about, we're electrifying to be sustainable. Well, yes, in some cases that's true, but that's not the only purpose for electrification. And remember, we had that list of motivations for electrifying an aircraft. There are a lot of things on here that could either be applied in the name of efficiency or lower operating cost. They could also be applied in the name of more maneuverability, higher redundancy, higher safety, lower noise, other things that aren't related to sustainability. And so electrification is not just sustainability. Electrification is how you get new types of aircraft that we can't have right now. However, the converse is also true. You know, misconception number 9, if we put liquid fuels in the electric aircraft, well then we're just completely negating the sustainability goals. That's not true either. You know, when we design these aircraft, we can design aircraft with distributed electric propulsion that are inherently more efficient to operate than a conventional aircraft. So right there, we can make something that consumes less fuel, that emits less pollutants. We can use SAF as the liquid fuel in these aircraft and get some pretty dramatic reductions in emissions. So even if we're using liquid fuels, we aren't negating the fact that we can achieve some pretty impressive results for sustainability with aviation using a hybrid electric approach where sustainable fuels come together with the benefits of electrification. So, this is one of the ones that I like. If sustainable aviation fuel is great and liquids are best for storing energy, is there even a point to these things? So, I've said a lot of things about batteries that aren't particularly flattering. Is there a point to these? This is kind of the flip side. I hear a lot of people talking about now batteries will never be useful, they'll never amount to anything. It's not necessarily the point I'm making, and this comes back to the right tool for the right job. And so let's talk a little bit about cars. Even though I said cars aren't very relevant, there are a couple analogies we can draw. So how many people here have heard about range anxiety in electric cars? How many people here have experienced range anxiety? I've experienced that driving towards a charging station a couple times. So I will say it's very real among electric car owners, and having flown a battery electric aircraft a few times, it's really, really real in the air. As you're watching it discharge, that's not fun. So range anxiety, not a good thing. And range is all about energy. But How many people in this room have been in a Tesla or an electric car when someone has really stepped on the accelerator and gone fast? That's impressive. I mean, you have like four-door family sedans that can out-accelerate a Ferrari. So there's something there. That's different. We never used to have that before in the automotive world. Well, acceleration isn't about energy, it's about power. And the only people with acceleration anxiety are the people designing gas cars right now because they can't compete with what the electrics can do. So this is interesting because it starts to hint at we've got a tool here that's useful, but maybe we're applying it the wrong way. So liquid fuels are really good at storing energy. There was that whole list of things that I had earlier. They get lighter as we use them and we can trade them off, payload for onboard energy. But the power you can get out of those liquid fuels, unless you light the whole tank of fuel on fire all at once, and that's not a good idea, power is limited by the size of the generator or the engine or whatever, and you can't just tell a 300 horsepower engine, yeah, you're a 300 horsepower engine, but why don't we run you at 1,000 horsepower for just a minute here and see what happens? It's gonna melt. Now, on the other hand, batteries are great at delivering power. You can have a battery pack that is delivering a nominal amount of power out, but then you can go to multiples of that level of power and pull that out for a short amount of time if you want to. That's something we could never do before with liquid fuels and piston engines or turbine engines. Now, the energy capacity of those batteries, that's that whole 20 times problem. That's a big problem. But power is really interesting. And so one of the reasons that hybrid electric systems are interesting is we allow both of these things to play to their strengths. We use liquid fuels to store the majority of the energy, or all of the energy in many cases, for the flight. But for cases where there are transient power loads or emergency situations, off nominal situations, maybe you want stall performance on a runway, situations where you need a bunch of power but not for very long, batteries are way better at that than liquid fuels and combustion engines ever will be. So it's not that batteries are bad or good, and it's not that liquid fuels are bad or good. They're tools. And I go back to that slide that I had with the hammer, the wrench, and the screwdriver. We have billions of dollars of hammers as wrenches and wrenches as screwdrivers going on in some cases in the industry, and we need to start thinking about how do we really practically use these things. So a 20 times energy deficit is really not great when it comes to using batteries as a primary energy source, never mind that other list of things that I had up there. But immediate power availability is really, really interesting. And I'll give you an example, a concrete example to think about. You look at all of these multi-rotor vertical takeoff electric aircraft, the Jobies, the Betas, Archers, things like that. The electric motors, one of the great things about them is they're very responsive. So you can quickly go from low power to high power back and forth. That helps you maneuver these aircraft really nicely. It helps you do the attitude control with the propulsion system. But because those things can all react really quickly, you can have very short duration transient spikes in your power demand where it goes way up and way down, and running that directly into a power generation system isn't a great idea. That causes you a lot of problems. Having batteries on board the aircraft that can buffer that and that can be complementary to the power generation system is a great thing. That is a great application of batteries. So batteries play a significant role in making electric flight possible. It's just not necessarily the role we all think that it's going to be. So the issues with batteries, there are a lot of people that look at all these issues that I just listed and say, well, they're not viable for use in aircraft at all. I'm pretty excited about batteries and how they can be applied. I just want to use them in the right way and as the right tool. So some conclusions. One is I think we all need to be aware that we're seeing this third major revolution in propulsion for electric aircraft. This is kind of like being around in aviation in the 40s, 50s, and 60s and getting to see, going from the DC-3 to the 707 or going from the P-51 to the F-104, drastic changes in what an aircraft looks like. But electric planes should look like electric planes. Generally speaking, we don't want to see turbofan 172s. We want to see things that are meant to be electric airplanes because that's how we're really getting those benefits, is making an electric plane that is unique and it is customized around the things that are great about electrification. Motors and power transmission are the big ideas. I would say as you're listening to people talk about what they're doing in electrification, the more they're talking about motors and power transmission and how they're leveraging the really cool aspects of those, and the less they're talking about batteries, that's a sign that I use that might be something really, really interesting that I want to pay a lot more attention to. Short-range flights aren't necessarily the enabler for batteries that we all want them to be, and that's just because safety, flight planning, all of those things come into play, regulatory compliance, and the result is reserve energy is what it is, and that doesn't get us around that. Batteries really aren't getting better at storing energy fast enough, and they need to get better in a whole lot of ways for us to really rely on them in most missions and most types of aircraft as the way we store the majority of the energy. Sustainable fuels and electrification, these aren't competitors in many cases, these are complementary. We're going to see those sustainable fuels flow through a hybrid system and power electric motors that do really cool things on aircraft that we could have never dreamed of having before. And so hybrids are not just a short-term enabler, hybrids are with us for 20, 30, 40, 50 years, as we look to close that gap, and some of those gaps with batteries are likely to never close. Batteries are never going to get lighter as they get consumed in general. But my last one on the list, batteries aren't bad. Batteries are a tool. Hammers aren't good or bad. Screwdrivers aren't good or bad. Wrenches aren't good or bad. Batteries have a significant role to play, but not for energy, for power, for situations where you need a lot of power right now and you have huge fluctuations in power. Batteries allow us to do things that we could never do before in designing an aerospace powertrain. So electrification is coming, but maybe not the way we expected it to play out originally. And we need to just remember, airplanes are not cars. And we all knew that. Everyone raised their hand and knew that at the beginning. And yet, I've seen billions of dollars flow through that logic process that says Teslas are cool, therefore we're going to make battery electric aircraft, and that's going to be really cool. So, right tool for the right job. Let's use motors and electric power transmission, focus on those things. And probably most importantly, let's start looking for what those electric aircraft are going to look like, because those are some of the early stages of electrification. There are probably things that no one has seen yet or that are behind closed doors right now that people are doing with electric motors and with power transmission. They're going to be really compelling, but in the end, a piston engine aircraft looks like a piston engine aircraft. Jets look like jets. Electric aircraft are going to look like electric aircraft for good reasons. So with that, I'd like to close my talk, and I'd also like to say, if you're interested in more information on this topic, we've got some hardware on display over at the AFWERX booth that's right across from Garmin. And Dr. Pat Anderson, who's the father of hybrid electric aviation and VerdeGo's Chief Technology Officer, is going to be doing a deeper dive into technically how do you assess the viability of different designs of electric aircraft. He's on forum stage 6 just down there at 10 a.m. tomorrow. So 2 great opportunities to learn even more. I'd like to thank you for being a great audience, and I'll take questions now. So thanks a lot. All right, I'm going to kind of rotate through the room, so I'll go with you first, sir. So let me rephrase the question so everyone can hear it, and let me know if I get it right. So one comment was kind of see the death of the conventional helicopter. The other was, what about fuel cells, and are those part of the toolbox? And I think the answer on the fuel cells is they might be, and it's worth researching them. So fuel cells have to have a high enough power density to be viable in an aircraft and not make it too heavy. And I think that's probably the metric that I would recommend watching. I'm personally kind of on the fence about, is that going to hit a tipping point or not? And we need to watch how the very skilled researchers that are working in that area, how they progress. But the key metric there that's either going to unlock that market or hold it back is the power density. For a given weight of fuel cells, can you get enough power going out of it at a steady state? Just to answer your helicopter point, I'm going to give you a contrary view to that, which is for most helicopter missions, I agree with you, because most of the time when a helicopter is used, you're taking off really quickly and transitioning into forward flight, and you're spending the majority of the flight going forwards and not hovering. In those situations, these new types of vertical takeoff aircraft can be vastly more efficient. But these new electric aircraft, most of those designs are a whole lot less efficient in hover. So if I was doing a search and rescue mission where I needed to hover over someone and maybe, winch them in the door of the helicopter, that's probably a great application for a helicopter and these aren't the right tool for that job. So it's a nuanced answer on that, but very good questions. So over here. So it's a good question, and just to rephrase it so everyone can hear it, question is, for smaller scale power plants, smaller output than this, which is in the 200 kilowatt range, do we at VerdeGo have something coming? The answer to that is not right now, because a lot of the interest and a lot of the economics driving the research in these programs has to do with things that are this size or a bit larger, and in many cases there are military applications for that. Now what that means though is we're maturing technologies and approaches and capabilities that can be scaled differently. So the work that we're doing now is undoubtedly accelerating the availability of smaller scale hybrid systems. But I can't say that we've got something in the works or that there's a timeline on that. And so it's good. I think it's going to be interesting to see when in this adoption of new technologies does that occur. And in addition to working with all these programs, I'm a general aviation pilot, so I'd love to see interesting applications of that. But I think that's a step down the road. So very good question. Over here. So the question was, if your mission is to move hundreds of people transcontinentally, basically, is there a reason to electrify versus just using conventional aircraft with SAF? And I would say right now, no. So right now, I would say the best way to do that and be more sustainable is to promote the SAF market, use the high efficiency turbofans that we have. The caveat to that is that Boeing or Airbus or Embraer or someone like that could choose to apply distributed electric propulsion to potentially create a more efficient architecture for an airliner. So if it's going to look like a 737 or an A320, it should have turbofans on it and put SAF in it. That's the right path forward. There are some, blended wing architectures with distributed propulsion controlling the boundary layer. I don't want to say that there's never going to be electrification or hybridization applied to airframes on that mission or that scale, but you would have to do it in a way that leverages that electrification to achieve something. So, good question. Over here? No, I get exactly where you're going. So the question is, cradle to grave, looking at, all of the different pollutants, the mining of materials, things like that, the chemistry inside a battery pack. And the best answers that I've seen on that are it depends on what you're doing. So it's not, and I know that that's a little bit ducking the question, but I think that's an important answer because it's not always better to electrify. It's not always better to do batteries. Sometimes it is in some missions, in some locations for some things. But there was a recent study that was really interesting that I apologize because I forget where it was. Someone looked at, if you're going to mine a certain amount of, minerals to create electric motors and battery packs, are you better off making a certain amount of electric cars, battery electric cars, or 10 times as many hybrid electric cars? Because you can use those batteries in two different ways. And it was a pretty clear cut that in a lot of cases, you'd get a lot bigger impact if you built 10 times as many hybrid electric cars with the same number of batteries, because that would actually reduce overall emissions way more than having just 1/10 as many electric cars. So it really does depend. It's not an easy question to answer, and certainly anyone who's positioning that it's just obvious, it's easy, we have to do this, it's greener, you have to get a lot more nuance than that. So, good point. Yep.
Right now, today, is there anybody using electric or hybrid electric in commercial duty service, say in Canada or Alaska, to deliver packages, maybe to areas where there's no liquid fuel, and size payloads that are comparable to a human being, hundreds of pounds, where you can get hydropower, solar power, wind power, and it's more economical and it flies in the drone, or is there nobody using it in that way at this time yet?
That's really not happening very much at this point, although a lot of the missions that you're describing, those look a lot like the missions the military is interested in right now, because they also operate in a lot of austere environments, and they, I think rightly so, appear to have concluded, and I'm not speaking for them, but I'm looking at the actions they've taken, they appear to have concluded that liquid fuels are so much more energy dense that you're way better off just putting a slightly larger fuel tank on these drones and having them be able to fly out and back than worry about solar infrastructure or something like that at the other end and doing batteries. That, a liquid fuel is so much more energy dense that you don't, one of the interesting things about a lot of the military missions is there is no energy at the other end of the mission. Like, you have to go there and you have to come all the way back before you get to refuel, and so that inherently makes them a lot harder.
You need a lot of power to take off on a short distance.
Correct. And again, that's one of those things where having some element of batteries in the powertrain, that's something they're really good at. So, yep, back here.
Say something about the weight comparison of a hybrid system. You consider the generators and the weight generators.
So I'll give you an anecdotal example that's probably as good as anything. So this power plant here is about 650 pounds. If you were to put that into a full powertrain, you would probably put that power plant alongside a battery pack that's maybe 100 pounds and a few hundred pounds of fuel. So all in, you've got a 1,000-pound powertrain. That 1,000-pound powertrain probably has the same amount of energy in it that 6,000 or 7,000 pounds of batteries would. So that's, when you're designing an aircraft, saying I've either got 1,000 pounds or 7,000 pounds of energy on board, that's a huge difference. So just compared to a piston engine, the piston engine is, about 60% of the weight of that overall unit, because we have a diesel cycle piston engine, runs on jet fuel in there. So the piston engine is approximately 60% of the total weight. The 40% is the other stuff that you put around it. So again, if something looks like a normal aircraft, don't put that in it. Just put the piston engine in it, because you don't need that extra weight. But if you've got an aircraft design that really benefits from electrification, or a mission that benefits from electrification, then all that weight easily pays for itself. So it's a nuanced approach. So in the back? So I'll paraphrase. I think it's kind of, where is this SAF coming from? Like, what is the feedstock that's making it, pull CO2 out of the atmosphere? And then why doesn't it get the same subsidies that things like ethanol or whatever get? So for the latter one, I don't know. I don't work in Washington, so I have no idea why they don't get the subsidies for that. You could probably make a pretty good argument that if one gets them, the other should. When it comes to what's the feedstock, I will say I'm not a chemist, and I don't even play one on TV, but there are 6 different feedstocks and processes for making SAF. And one of the challenges that the sustainable fuels market has, I talked a lot about the challenges in batteries and some of the misconceptions. So there's this term SAF, S-A-F, Sustainable Aviation Fuel. And that's broadly put across all of these different ways of making basically manufactured jet fuel. Some of those are green and some of those may not be really green. And so there's a bit of a branding problem that industry has, where there are some people doing things like, converting waste stock and garbage and things like that into fuels. That's pretty interesting from a sustainability standpoint. There are also people working with crops that they probably shouldn't be working with, that aren't really the right feedstock, and it's debatable whether that's sustainable at all. So that'd be a whole separate presentation to this, but it's another thing where, just like with electrification, there's some really good stuff going on, but there's also some weird misconceptions. The SAF market, there's some really good stuff going on, and then there's some also things you got to watch out for. So, yep. All right, other questions, comments, assertions, demands? Back here first. So the question was, what kind of timeline do we see hybrid powertrains going out? So I guess one of the answers, there are a lot of ways to answer that. One of the answers I like is we shipped our first ones out about 1.5 years ago. For some applications behind the scenes, I would say you're going to see more and more of this going into effect, particularly in the drone market. That's an area that's likely to lead. A lot of the news that you see and the things that get these trillion-dollar headlines are things like urban air mobility, which is really cool, which probably works. It's also probably the hardest thing you could choose to do with these new technologies, because you're talking about paying passengers on commercial flights in vertical takeoff aircraft that are new configurations we've never done before, propelled by new technologies in urban areas. So if I had to pick something hard, that would be it. What is a lot lower hanging fruit is, for example, almost all of the branches of the military have an urgent need for unmanned autonomous delivery of urgent cargo to forward deployed locations. That's a really big need, because right now the smallest increment of transportation tends to be a Black Hawk helicopter. And a Black Hawk is big and expensive, but also it has 2 people on board. And that gets you into some really tough decisions where you have to decide, these people out there, these soldiers out there, they need stuff urgently. They need medical supplies, food, water, ammunition, whatever. Maybe they need a medevac. Are we better off sending more people into harm's way, or are we better off not sending in what they need? That's a terrible decision to have to face. If you have autonomous drones that can lift hundreds of pounds of cargo and go 50 miles from a safe location to another location, if you lose a few of those, does it matter? Yes, they have a value, but but all of a sudden it flips that equation operationally for how you look at when do you choose to send the mission out and when do you not. So, your question was, when will we see these things go into service? In applications like that, I think it's in a matter of a few years. It's coming soon. Yep. So that's a really interesting question, and I will say there's a big demand right now for really small hybrid systems. And there are also some real challenges as you scale things down smaller. With a lot of aviation technologies, you have to look at what scales and what doesn't. It's a lot harder to do that weight effectively for the really small stuff than the bigger stuff right now. So I think that may be on the way, but I'm also not sure that that's going to be quick, because there are some things that are harder about doing it small than doing it big. The other thing, and this gets outside of the topic of hybridization or electrification, it's really hard operationally to figure out how you land something or drop off packages aerially at a specific address. So, when the military wants to send a drone in and have soldiers on the other end to meet it and clear out an LZ and stuff like that, you can conceive of how that works. In residential neighborhoods, you have dogs and bicycles and swing sets and trees and all kinds of crazy things to maneuver around. That's a really hard autonomy challenge to figure out how do you, it's not the last mile, it's like the last 50 feet of the mission. How do you do that? And that's hard. So, good question. So, we are coming up on the time limit here, and so I'm sure there's going to be another speaker wanting to come up here momentarily, and if the next speaker is in the room, please come up and push me off the stage. Otherwise, I'll keep taking questions. I think that does wind up proving true on the electric motor side. That's one of the things about electric motors that is amazing. And it's one of the reasons why we're willing now to put 4 or 8 or 10 propulsion units back on an airplane, because you would never want to do that with piston engines or turbines. I mean, the aircraft would be in the shop all the time. So that aspect of it, yes. Now, when it comes to the hybrid power generation, I think what we're looking at is basically something similar to the TBOs we've got now. I mean, we're talking about piston engines or turbine engines that are known quantities driving generators. So it's going to be, depending on the piece of the powertrain, as good as we are now or better, and it kind of depends on what end of the powertrain you're talking about. Yep. All right, I think I'm going to wrap it up there, but I'll be around somewhere near the front if you've got any other questions, and thanks for being a great audience.